Now we have David Kosower, who will talk about from waveforms to amplitudes. Thank you.
Thank you, Filippo, and thanks for the opportunity to speak at this meeting, which is unfortunately dominated by very small things, even though we're mostly interested in very large, compact objects and ultimately in binary systems of them emitting gravitational radiation. Now, I'm going to talk about an approach, or one of a variety of approaches that's emerged in recent years for computing, ultimately computing gravitational radiation based on quantum scattering amplitudes. And the first thing I want to try and motivate is why you would even think about that, because ultimately it's a bound state classical problem that we're interested in. So why would you even think that something from deep in the quantum regime, something above, at least starts life above threshold, would be of any use at all? Well, part of it is not just the scattering amplitudes themselves, but also the whole technologies that have been developed in the last 20 to 25 years for computing them, namely focusing on kind of the minimal computations and computing only what's needed for physical quantities. In our context, that would mean we could get rid of Hamiltonians, potentials, Lagrangians, if we wanted to. But the real promise here is that of the double copy. And basically the observation that if you know how to compute in Yang-Mills, so theories like QCD, then calculations in gravity are vastly simplified. And that's thanks to the so-called double copy relation, which one can heuristically phrase as the idea that gravity amplitudes are, in a sense, like Yang-Mills amplitude squared. And just to give that a more concrete picture for you, if we look at the 3-point amplitude in a Yang-Mills theory, having stripped the color degrees of freedom, then we end up with this simple expression here. I hope my mouse is visible. And for those of you who don't know, these angle objects are basically square roots of their spinor product. So they're basically square roots of Lorentz invariants. And at the 3-point level, the statement that gravity is like the square of Yang-Mills is literally true. Once you strip the coupling, then the gravitational 3-point amplitude is literally the square of the Yang-Mills amplitude. And there are generalizations of that that allow you to compute at tree level and then integrands at loop level. And this is, in a sense, the field theory equivalent of the famous Kawai, Llewellyn-Tai expression that relates closed string amplitudes to open string ones. So a lot of the traditional GR activity is in the post-Newtonian framework, non-relativistic. We have an expansion parameter, which is then variably related to a potential measurement. And we can have both integral and half orders in this expansion. One can also do what us in quantum scattering amplitudes would call just the plain perturbative expansion, just in powers of G. And for somewhat obscure reasons, this has gotten confusingly renamed the post-Minkowskian expansion. So I'm not going to use that term. I'm just going to think about expansions in G. But for those of you who are used to the other language, that is what it is. We're also used to thinking about conservative and dissipative or radiation reaction contribution separately, and the potentials essentially are focusing on the first, but in this approach, we're really thinking about doing both together. We're not separating. So there are a number of groups who have worked on this, and maybe the most widely publicized is that of Zvi Bern and his younger collaborators, whose names I really should be mentioning. And that's basically computing a scattering amplitude in effective field theory and then matching that to the full amplitude computed using these double copy tricks. And this, of course, builds on pioneering work of Walter Goldberger and Ira Rothstein. There are people who have extracted the potential by looking inside the scattering amplitude, and then you can take these potentials and feed them into the effective one body or other formalisms in order to compute corrections to gravitational radiation. There's also been people who have thought about effective actions, iconal approaches, world line approaches. And what I'm going to try and outline here is maybe what I would call a more scenic route. So if I'm choosing not a scene from Paris, but from somewhere in the south of France, that's what it might look like. And our philosophy is as follows. We want to pick well-defined observables in the quantum theory. We then want to, and observables that are also, of course, relevant in the classical limit. And then we want to understand how to express them in terms of scattering amplitudes in the quantum theory, and then understand how to take the classical limit efficiently. And in the long run, there are clearly going to be shortcuts, but this allows us, has in fact certain advantages, because the quantum theory knows things that the bare bones classical theory doesn't quite know. And recently people have actually started to apply these ideas to more frontier calculations, particularly in the context of SUSY theory, to loop or NNLO calculations of the impulse. So I'm going to explain the general setup, and then towards the end, assuming I don't get cut off by our chairman, I'll talk a little bit about kind of current work in progress. I should have mentioned that this a lot of this background work was done with Donald O'Connell, who's at Edinburgh, and his then graduate student Ben Mabey. And some of the more recent work is being done with two graduate students in Dublin and in Copenhagen, Riccardo Gonzo and Andrea Cristofoli. So we're going to focus on above threshold here, and leaving the extension to bound states to future work. There's been some progress in that direction by Rafael Porto and his collaborators, but I'm not going to talk about that here. So we're scattering two massive particles, and we're going to look at, we could look at some observables. The one I'm going to look at here is the radiated momentum. So we're going to imagine scattering charged particles in QED, or perhaps scattering massive particles and then looking at the gravitational radiation. So we're going to look at the radiated momentum and at the wave amplitude. And you could also compute the momentum transfer, and from that extract geometrically the scattering angle. Now, we all love scattering amplitudes, or at least those of us coming from the amplitudes community do, but we do have to remember they're not the final goal. They're not physically meaningful on their own. So what we really care about is computing observables. And in our present context, of course, in scattering amplitudes, we're used to working with plane wave states, but here we actually need to form localized particles. So we need to have, we're trying to mimic point particles. So we need localized positions and localized momenta. We do that by introducing a wave function, which I'm using the lowercase phi notation for. And our initial state is going to be built through an integration over the on-shell phase space of the incoming particle. So we integrate over P1 and P2, that's our two incoming particles. This is the complete initial state. There's on-shell positive energy delta functions. There are the two wave functions for those particles. And then those wave functions are built by superposing plane wave states, which are the usual incoming plane wave states. And then we have an impact parameter. They're not going to be colliding head on, and that's encoded in the space vector. And at some points I will use a somewhat more compact notation, and also all the hats here are there to hide the two pi's that would either be scattered around. Of course, in the final answer, we need to bring them out. So we want to take the classical limit that involves taking h bar in the limit towards 0, although not substituting h bar equals 0. So the first thing we have to do, since usually in quantum field theory, we set h bar equals to 1, we have to restore h bar. On the other hand, we still want to do things fully relativistically, so we're going to keep c equals 1. And the simplest way to restore h bar is just to do dimensional analysis. The net effect is that mass is no longer inverse length, but we can keep the usual normalization of states, and that means that the usual dimensions, I should say, of amplitudes stays the same. It's a mass dimension to 4 minus n. The big change at this stage is that we essentially have to make manifest the h bars that are present in couplings, and mercifully both the gravitational and electromagnetic coupling behave the same way, so we can think of them generically with a little letter g that I'll use. The other thing that will turn out to be important is to distinguish wave numbers from momenta. Again, if h bar is equal to 1, they're the same thing. Here they are not. And I'll use the overbar notation to label wave numbers, and momenta will be labeled without the overbar. So if we now kind of shake this up a little bit, then we discover that in QED, for example, an endpoint L-loop amplitude scales as h bar to the 1 minus n over 2 minus capital L. So yes, indeed, if you just do this naively and you just think about looking at the amplitude, then it is singular in the h bar goes to 0 limit. And of course, that's not the whole story, but some people do get confused, so to point that out. So now, as I said, we're not just interested in the amplitude itself. We want to compute physical observables, and one example of a physical observable is the total radiated momentum, and photons and gravitons together I would sometimes call messengers. And so we just have to form the momentum operator is this bold k. We have to look at its expectation value in the outgoing state. Now, of course, what I wrote earlier was the incoming state, but they're related by the S matrix, by the scattering matrix. You can think of that as an evolution matrix from negative infinity all the way to positive infinity. And the S matrix itself, you can write as 1 plus IT, T being the transition matrix. Of course, the one term will disappear here. There's no momentum of photons or gravitons in the initial state. And so we'll end up with this expression here, which is quadratic in the T matrix, which is to say ultimately then quadratic in the scattering amplitudes. Now, there's two different momenta that we will find because there's two different integrals for the different copies of the initial state. And so there's a momentum mismatch between those two copies, which I'm going to label Q. And it looks in some cases like a momentum transfer, but it isn't exactly the same thing. Now we can actually put in a complete set of states in between these, the T dagger and the T somewhere. And then we can see that our expectation value here of the radiated momentum does in fact have the form of an integral over the intermediate state, measure the momentum, and then it's either a cut of an amplitude or an amplitude squared. And both these expressions are valid to all orders. They're kind of basis formulae, which you can now start to expand in perturbation theory. So if you want to think about it diagrammatically, we'd have some over states and on-shell integrations, their energy momentum conserving delta functions, and then you have a product of two scattering amplitudes. And the red K here is let's say the distinguished momentum, and then there could be additional particles, additional photons, for example, as you go to higher order. So we now have to continue taking the classical limit. We've built these wave packets, these localized wave packets, and there are actually three different scales that we need to think about. There's the Compton wavelength of the particle, there's the kind of intrinsic size of the wave function. And then there's the separation, the impact parameter, the separation between our two particles as they whiz by each other in the scattering. So we want the particles to be very well localized. That means that we have one deep inequality, the Compton wavelength being much less than the wave packet spread. And we also want the wave packets themselves not to overlap. Otherwise, we're inevitably going to get quantum effects. So the wave packet spread has to be much smaller than the impact parameter. That together, we get what I like to call the Goldilocks condition. And you can do a much more detailed analysis that essentially gives the same result. So I'm not going to go through that analysis in detail, but I'll just sketch it a little bit. You have, again, these two copies of the incoming state, and they both represent the particle. We want them, on the one hand, to be sharply peaked. On the other hand, we want them to be basically completely overlapping. And that ultimately gives you a constraint on Q squared, on this momentum mismatch. In fact, it's necessarily space-like, so we can, it's minus Q squared is a positive quantity. And if we just express it in terms of the momentum mismatch, then we discover there's an H bar there. The natural thing to do is to remove that H bar by going to wave numbers, and then the actual condition is independent. Minus Q bar squared is essentially the same as the impact parameter squared. So this, you can see already, is 1/2 of the Goldilocks condition. And so one of the other things this analysis teaches you is that the natural integration variables for the messenger momenta, that is the photons and the gravitons, are wave numbers, not momenta. And that's true for this mismatch. It's true for real momentum transfers that would happen inside the scattering amplitudes. And it's also then true by unitarity for the loop momentum, where we're integrating over messengers inside loops. And that in turn means that from the measures of integration, there will be more factors of H bar to extract. So if we summarize this analysis, then we're going to extract the H bars in the coupling, extract the H bars in the messenger momenta, and then we have to take the H bar goes to 0 limit. In general, we may have to do a Laurent expansion because there can be singular contributions. That turns out not to be the case at leading order, but at higher order, there are in fact terms which will cancel. At least when you're doing physical observables. And finally, you then have to integrate over the massive phase space and do the replacement of the momentum by the mass times the Four velocity. So as just an example, if we look at the total radiation, then that is in fact, from the point of view of the scattering, a next to leading order effect. So the leading order radiation shows up at order G to the 6th. And that corresponds to integrating over a 5-point tree amplitude. The coupling gives us the various, well, I should say actually the coupling will hide various factors of 1 over H bar. From the measure, we get compensating factors of H bar in front. So when all the dust settles and we express the integration over the wave number, then we find that there are no H bars, and this has a well-behaved classical limit. This R object is essentially the classical radiation kernel, although here we've obtained it as the limit of an amplitude. At tree level, there's not really much to do. You essentially replace the propagators by their iconal versions. And so if one evaluates this, for example, in QED at leading order, then you find a relatively simple expression, and of course matches the classical result. In fact, it's in some sense more intelligent than the classical result, because at this order in the classical field theory, you would need to add the Abraham-Lorentz-Dirac force in order to conserve momentum. Of course, the quantum theory knows about momentum conservation. It's built in, so it has this ALD contribution built in. Now, we want to, of course, not just look at the total integrated radiation. We would have to have a 4-pi detector, which would be difficult enough if we were in a lab doing E&M experiments, and it would be completely hopeless in gravitational waves. So we want to look instead at what one might call a local observable. So we have some scattering process that's happening somewhere, and then there's radiation that's propagating towards our observer, here denoted by this caricature of a pair of eyes in some direction. So we can then write our observable here as a function of x as the propagation of some scattering event that happens in that region, and there are indices that can be carried by the radiation, be one index in the case of photons, 2 indices for gravitons, and the waveform is the leading large distance behavior of this propagation. So that's what we're ultimately be interested in extracting. It's essentially given by a Fourier transform. There's actually 2 times here. There's the clock time and kind of the observer's time, and that's related to the fact the absolute phase is not observable, but the relative phase between nearby observers is. And so what we need to do here in the E&M case is to measure the E&M field. In the gravitational case, we would measure something like a Weyl tensor. And again, we can write out that observable. We're measuring the field in the outgoing state. We can write the outgoing state in terms of the incoming state using the S matrix. We now expand the S matrix and we get a few terms. Of course, in the initial state, we're not putting in any radiation. So one of these terms drops out, but then using unitarity, we can write the expected field. And again, this is x dependent, so we can look at it in some specific direction. There's a commutator term, and then there's a term which is quadratic in the transition matrix. And I didn't show you the expression for the momentum transfer, but it's very similar in structure to that expression. Leading term here shows up at leading order, which is g cubed, and the next term shows up only in the higher order corrections. So now we can work this out. We can simply write out what this expression is using our wave function. We just substitute in, again, these capital Phi's are just the on-shell phase space measure. We have our impact parameter, and then we have the various matrix elements that arise along with the momentum and polarization vectors that are linked to the insertion of the field operator. And what one discovers is that here, instead of getting this kind of averaging over the square of the classical radiation kernel, here we essentially just get the radiation kernel. And again, in QED, we can carry out these integrals. You get a set of delta functions. And if you happen to have a whole string of these scatterings happening one after the other, and you transformed them into the audio spectrum, then you might get something that sounds a little bit like this. I hope that sound is actually coming through. So up to this point, we've actually considered the scattering of massive point particles, but we can also think about the limit of massless particles. So if we imagine scattering, let's say, a photon off of a massive particle. And what we expect is that we would get a classical wave as a limit. And that's roughly what happens. So we can write down an expression for the quantum field, and I'm writing it here for the photon. One could write down an analogous expression for the graviton. sum over incoming and outgoing modes. Again, there's an on-shell phase space integral. And it turns out that the right language for talking about these limits is that of so-called coherent states, which have been used for a long time in quantum optics. And the natural states that have a classical limit are these coherent states. And in fact, the classical field you can think of as the expectation of a coherent state, of the field operator in a coherent state. And that's so long as you're working in the limit of very large occupation number. So if the number of photons gets very large, then the correlation term that would exist between two quantum fields goes to zero as h bar. And just here, before I put up my summary slide, one can also test this factorization property on the outgoing radiation, and one can show that it also forms a coherent state. So this spectral function corresponds to a coherent state in the outgoing state. And with that, I won't tax the chairman's patience, and I'll put up my summary slide. So we have new demands on theoretical calculations, and there's an opportunity to use scattering amplitudes here that's ultimately driven by the simplification afforded by the double copy for gravitational amplitudes. And we've organized a formalism to start with quantum observables and obtain classical results, counting the h-bars, and then applying the simple rule of using momenta for massive particles and wave numbers for massless particles. And the other message is that, in a sense, the waveform for radiation at its lowest order is just a 5-point scattering amplitude. And I'll stop there.
Thanks a lot, David. So we have time for questions. There's one question from Luke.
Hello. In your first slide, you refer to as the post-Newtonian approximation as non-relativistic. And I must say that for me, it looks to be shocking for me, because when you go to high order, the equations of motion that you get and the radiation field are relativistic in the sense that the Lorentz invariance, Lorentz-Poincaré invariance is satisfied, of course, in an approximation way, but up to high order. In some coordinate systems, the Lorentz invariance is manifest. In other coordinate system, it is not manifest, but it is still there. There are some, there is a Poincaré algebra. You can construct phase space generators which realize this algebra. So for me, it is relativistic up to high order, consistently with the approximation, of course.
Well, I mean, I think at this point we're starting to split hairs here. I mean, to get a fully relativistic answer, one where you can take the velocities as close as you like to the speed of light, you'd have to do a resummation, which is, I think, also implicit in what you're saying. So I think maybe we have a difference of viewpoint or language here.
Diego?
Hi, can you hear me?
Yeah.
Yeah, I wonder from the results that you showed, which is the advantage of this new formalism? I know that, yeah, I know these results that they allow you to go very high in this post-Minkowskian, but for what you showed in this talk, is there any, what are the new, what are the new insights for the classical calculation or something going on?
Well, I mean, the purpose here is to outline the formalism.
Okay.
I'm not showing any new results here. I mean, the promise here, in a sense, is that of making use of the double copy. And so, as an example, it's the scattering waveform, or at least the scattering radiation at leading order, was computed by Kovacs and I hope I'm pronouncing that correctly, and Thorne I think about 40 years ago. And that's a calculation which, well, I would say is a lot easier to reproduce than theirs. It's essentially a tree-level 5-point scattering amplitude with some integrals decorating it. And it's certainly feasible to take that to one loop, all to next to leading order. That's the corresponding one loop amplitudes. That technology is well understood. And it's possible, although non-trivial, to take that to 2-loop order. That would be a 2-loop 5-point computation, which people are doing now, although it is a frontier calculation. I think those two calculations would be extremely difficult, as my understanding, in GR. So that's kind of an example of where things can go in the next 2 to 3 years.
Thank you.
Okay, if the questions can be very, very fast, Uri?
Yes, it is. I hope that it is fast. I would like to know if with this scattering method can be distinguished between a classical graviton, let's say, and a quantum graviton. I don't know, finding something like a structure function or something. Imagine that there is no effective quantum graviton. And for instance, in gauge gravity models, gravity is actually a sort of vector field. Can we distinguish between these two types of models?
Well, I guess my answer there, I will try to keep it brief. But first of all, whatever quantum theory you have of gravity has to produce GR as a very low energy limit, because otherwise it disagrees with long-standing observation. So you would have to produce the same classical results that are being produced here. This expansion could be carried out systematically in H-bar. So you could, if you were interested in compute the next corrections. And of course, those corrections would ultimately depend on what quantum theory you're starting with. So they would differ if you had Einsteinian gravity, let's say at the Planck scale, or if you had string theory, or if you had something else. And then the question would be, would the physical observable actually vary enough to be detected? And conventional models of black holes would say no, but I do have, and actually Filippo, I have a colleague or colleagues actually, who have been working on these models of black holes that are superpositions. And I'm told, although I haven't looked in detail, that LISA predictions would actually depend on their models, and you would be able to see the differences. So you would compute here the OR corrections, and you would find that they can actually be seen by LISA. So that would be how you do it in this formalism.
Okay.
Okay. So thanks a lot, David. I suggest that we stop here.